Hello students, yesterday we discussed about carbohydrates, classification and different types of saccharides. So today we will be talking about monosaccharides, as we have already discussed that it is the simplest carbohydrate and it cannot be hydrolyzed further to any smaller molecule or any smaller monosaccharide. The most common monosaccharide is glucose, having a general formula of C6H6O6 as shown in the slide. Glucose is most widely distributed monosaccharide in all the fruits that we eat. It is glucose which is present in the larger amount. So it is most widely distributed monosaccharides. Glucose is also known as grape sugar and it is present in very high amount in ripe grapes. We also call glucose as dextrose because it is dextrorotatory. It rotates the plane of polarized light towards right. So we will discuss about it in later classes. So in the combined state, glucose occurs as either glycosides or as disaccharide or as a polysaccharide molecule. So there are some other monosaccharide molecules also, like fructose, mannose, galactose, arabinose, etc. There are many monosaccharide molecules. Up to like 20 monosaccharide molecules exist in nature. Structure of glucose is as shown. It is a 6-carbon molecule having 4 cardinal centers. At the top of this particular molecule we have a free aldehyde group, and at the bottom we have a CH2OH molecule. Alright, since it has a free aldehyde group and there are many hydroxyl groups, so this particular molecule, it shows reactions which are given by aldehyde group as well as by hydroxy group. So both the reactions are possible with this particular glucose molecule. Now first, since we are discussing about glucose, so let us look at the reactions which glucose molecule can show. The first reaction is with the aldehyde group. At the top we have a CHO group, which is the aldehyde group. So it will show all the typical reactions of an aldehyde group. First is with when we react it with HCN. HCN is hydrogen cyanide. So when we react a molecule of glucose or any molecule of a monosaccharide, when we react it with hydrogen cyanide, it forms cyanohedrin, right? Because it is what? It is a carbonyl compound. At the top we have an aldehyde group, and aldehyde group belongs to the carbonyl family. So carbonyl family molecules, they react with hydrogen cyanide, in which cyanide molecule acts as a nucleophile. So basically this cyanide nucleophile, it attacks the carbonyl carbon. Alright, it is a nucleophilic substitution reaction. The cyanide ion attacks the carbonyl carbon and forms a molecule of cyanohydrin. Alright. So this is a very typical reaction of formation of cyanohydrin. Any carbonyl molecule will respond to this particular reaction, be it an aldehyde or a ketone. But this glucose molecule, it does not react with Schiff's reagent and it does not form addition compound with sodium bisulfite saturated solution. So Schiff's reagent के साथ reaction नहीं होता, जो कि एक टिपिकल ऑल्डिहाइड ग्रुप जो होता है वो शिफ्ट रिएजेंट के साथ रिएक्ट करके कुछ प्रोडक्ट फॉर्म करता है, एडिशन प्रोडक्ट फॉर्म करता है. लेकिन ऑल्डिहाइड्स कार्बोहाइड्रेट्स दे डू नॉट रिएक्ट विद शिफ्ट रिएजेंट because of some of the structural restrictions. The next reaction is with hydroxylamine. Hydroxylamine is NH2OH. Okay, so it also reacts with hydroxylamine and forms oxime. It forms glucose oxime. As we can easily see, we have CH double bond NOH. ठीक है, तो ये जो CH double bond NOH molecule है, this is oxime. So these reaction with hydroxylamine gives us oxime. All right. So next reaction is reaction with phenylhydrazine. Phenylhydrazine is NH2NH C6H5, and upon reaction with restricted amount of phenylhydrazine C, In this case, we have taken only one molecule of phenylhydrazine. So upon reaction with only one molecule of phenylhydrazine, it forms glucose phenylhydrazone. As shown in the structure, you can easily see. Okay, so just a second. Okay, I'm sorry. Just let it be. I don't know how to remove it. Okay, yeah. So next topic is osa-zone formation. Osa-zone formation is a very important topic, as we discuss about glucose molecule. Glucose forms a addition compound which is known as osa-zone. Not only glucose molecule like fructose, mannose, they all form osa-zone. Basically, this is a reaction which is shown by alpha hydroxyaldehyde or alpha hydroxyketones or some molecules, some carbohydrates which has a free aldehyde group. They respond to this particular reaction, they form osa-zones. Osa-zones are bright yellow crystalline compounds. They are solid molecules, and it is a very typical reaction which is given by carbohydrate molecules, mostly monosaccharides. Okay, so in osa-zone formation, what we do, this is a reaction with the phenylhydrazine, but in this case we do not use a restricted amount of phenylhydrazine, rather we use excess of phenylhydrazine. So as we can see in the slide also, this is a glucose molecule. So this glucose molecule, it reacts with 3 molecules of phenylhydrazine and it forms this particular structure which is labeled as glucosazone. So we have CH double bond N, NH, C6H5. So addition of pH is occurring at carbon number 1 and carbon number 2, and along with the removal of a molecule of aniline and a molecule of ammonia. Alright, so all the reducing carbohydrates, they respond to this particular reaction which is osa-zone formation. So as I already told you that all the alpha hydroxyaldehydes and alpha hydroxyketone, they respond to this particular osa-zone formation reaction. They all form bright yellow crystalline compounds. The time of formation of this osa-zone formation may differ as per the carbohydrate which we are taking. Now there is a very important point about this osa-zone formation, that during this osa-zone formation, the stereochemistry about the carbon number 2, what is carbon number 2? That is this particular carbon. Alright, the stereochemistry about the carbon number 2 is destroyed. As we can see that that this particular carbon is chiral. So upon formation of osa-zone, the chirality of this carbon is destroyed. Now as we can say that carbon is no longer chiral, because it is forming an addition compound with phenylhydrazine and forming a double bond. So double bond form हो रहा है, इसलिए chirality इसकी destroy हो गई. तो destruction of chirality, but the configuration of rest of the molecule does not change. The molecule retain its configuration. Alright, this is a very important point from stereochemical point of view. Now for the explanation of the formation of this glucosazone molecule, there are 2 different mechanisms are proposed. First mechanism is Fischer's mechanism, and second is proposed by Weygand, and it involves the Amadori's rearrangement. So Fischer was the very first person, Emil Fischer, who prepared the osa-zone in laboratory, and he proposed a mechanism. He gave a series of reactions through which osa-zone can be prepared, but its mechanism has certain drawbacks which we are going to discuss. So because of the failure of not able to explain some of the points, this second person, Weygand, came into the picture, and he gave an Amadori's rearrangement mechanism which fully explained the formation of osa-zone. Now what is Fischer's mechanism? In case of Fischer's mechanism, 3 molecules of phenylhydrazine reacts with 1 molecule of glucose or any other carbohydrate, but these carbohydrates, they should be differing at configuration of carbon number 2. Now this is the reaction for Emil Fischer mechanism. the first one to prepare, he was the first one to prepare osazone. As we can see, this is the structure of glucose molecule. This is the structure of glucose molecule. We have at the top, we have a free aldehyde group, CHO, and this is how the hydroxyl groups are arranged in the glucose structure. We have 3 hydroxyl groups at carbon number 2, 4 and 5. The hydroxyl groups are present on the right hand side, and at carbon number 3 the hydroxyl group is present at left hand side. So this is the actual structure of glucose molecule. We call it as D plus glucose. So why D plus glucose? I will be covering in the next classes. First of all, let us look at the mechanism. So this glucose molecule is reacted with, first of all, one molecule of phenylhydrazine. Actually it reacts, while doing the reaction, we put excess of phenylhydrazine hydrochloride in the reaction vessel. So but initially this molecule reacts with only one molecule of phenylhydrazine and forms this particular intermediate, this particular intermediate. Then this particular intermediate, it forms an addition compound with a hydroxyl group. Then again this addition product reacts with another molecule of phenylhydrazine and it oxidizes the carbon number 2, forming carbonyl carbon at second position. Again the third molecule of phenylhydrazine came into picture and gives glucosazone, which is this, as the product. Okay, so this is the mechanism proposed by Fischer. Now this Fischer mechanism has certain drawbacks. The first drawback is phenylhydrazine is a very strong reducing agent. Okay, phenylhydrazine is a very strong reducing agent, but in this case, in the second step, when the second molecule of phenylhydrazine is added, it does not act as a reducing agent, rather it acts as an oxidizing agent, oxidizing the second carbon into carbonyl group. So this is not proposed, this is not very well explained by this particular mechanism. And in the second step, that is the addition of phenylhydrazine, it occurs at only first 2 carbons, as we can say that the addition is only occurring at the first 2 carbons, right? Only these 2 carbons, and rest of the carbons are left untouched. Why such partiality is being done? Why only first 2 carbons are treated as privileged and the rest of the carbons are ignored? So the reason for this is not explained in the Fischer mechanism. So to understand what is actually happening and why only first 2 carbons are being attacked by the phenylhydrazine molecule and rest of the molecule retaining its configuration, this was actually very beautifully explained by Amadori's rearrangement. Now what is Amadori's rearrangement? In this particular method, after the addition of first molecule of phenylhydrazine, a rearrangement occurs. Okay, so a rearrangement of a type of tautomerism. There is a tautomerism. What is tautomerism? We have seen keto-enol tautomerism in first year. In your previous classes, second year में भी explain हुआ होगा, first year में भी आपको पढ़ाया गया होगा when we were doing stereochemistry. So in tautomerism, we can convert a keto group into an enol group by interconversion of hydrogen atoms. So such type of tautomerism is also occurring in this case between the first 2 carbons. Okay, and after the tautomerism, it forms an intermediate, which is a 6-membered intermediate, and the intermediate is stabilized by hydrogen bonding. All right, so after the formation of the intermediate, it expels a molecule of aniline and a molecule of ammonia from the intermediate structure, and it gives you an aminoketone, which is another intermediate, and this aminoketone, it reacts with another 2 molecules of phenylhydrazine and finally giving us the much desired osazone. So this is the reaction. This is the reaction which is showing the Amadori's rearrangement. So we have our glucose molecule. In this glucose molecule, we are taking labeled phenylhydrazine. Why we are taking labeled phenylhydrazine? Just to know the exact mechanism, that the very first phenyl hydrazine which is being added to the glucose molecule is expelled in the form of ammonia. To have a detailed understanding of the mechanism, we are taking one of the molecule as labeled phenyl hydrazine. So this labeled phenyl hydrazine, it forms an addition product with the glucose molecule, which is shown by this particular structure. After the formation of this particular structure, there is a rearrangement occurring. As we can see in this particular structure, there is some rearrangement. This nitrogen is forming a hydrogen bond with the hydrogen atom of the second carbon. Alright, so you can easily see the bonding over here. So this is the hydrogen bonded 6-membered intermediate. One is CH, double bond COH, NH, NH. So we have formed a 6-membered intermediate. So because after the addition of one molecule of phenyl hydrazine, a 6-membered transition state, or we can say a 6-membered hydrogen bonded intermediate structure is formed. So, and this is possible only in case of first 2 carbons. So reaction occurs as only first 2 carbons. So after the intermediate formation, a molecule of aniline comes out and we get aminoketone as the intermediate. Now this aminoketone again is treated with another molecule of phenyl hydrazine, and it forms this particular intermediate. Okay, this intermediate is being formed, which further reacts with another molecule of phenyl hydrazine and thereby giving us the much desired osazone, and the unlabeled having the unlabeled phenyl hydrazine, and the labeled one is expelled out in the form of ammonia. Okay, so this is the overall mechanism which shows the Amadori's rearrangement. Amadori's rearrangement is very well explained by this particular structure. So this mechanism shows why reaction occurs at only first 2 carbons, but it does not show why the reaction stops after the addition of first 2 carbons and no further additions are being taking place. तो फर्स्ट 2 कार्बन पे क्यों हुआ? क्योंकि एक इंटरमीडिएट बन गया. उस इंटरमीडिएट की वजह से हमारी रिस्ट्रिक्शन हो गई कि फर्स्ट 2 कार्बन पर ही वो ऐड हो रहा है. बट बाकी के कार्बन पर क्यों नहीं ऐड हो रहा? दिस will be explained by the following structures. This is the structure of osazone. Okay, let us look at the structure of osazone. So this is the osazone structure. In this osazone structure, this osazone structure is forming a 6-membered intermediate. So it is forming a chelate. Okay, चीलेट बाय हाइड्रोजन बॉन्डिंग. यहाँ पे नाइट्रोजन और हाइड्रोजन के बीच में हाइड्रोजन बॉन्डिंग हो रही है. ये जो आर ग्रुप है ये यहाँ पे हमने बता रखा है, ये रेस्ट ऑफ द ग्लूकोज मॉलिक्यूल है. तो यहाँ पे एक हाइड्रोजन बॉन्डिंग हो गई. तो कार्बन नंबर 1 और कार्बन नंबर 2 पे जो हमारे ये NHC6H5 ग्रुप जो हमारा लगा आके ओसाजोन का, ये एक दूसरे से हाइड्रोजन बॉन्ड के थ्रू अटैच हो रहे हैं, एक दूसरे को स्टेबलाइज कर रहे हैं. तो क्योंकि 6-membered एक इंटरमीडिएट हाइड्रोजन बॉन्डेड स्ट्रक्चर फॉर्म हो रहा है इन ओसाजोन, सो दिस गिव्स द स्ट्रक्चर एन एक्स्ट्रा स्टेबिलिटी. तो एक्स्ट्रा स्टेबिलिटी मिलने की वजह से दिस पर्टिकुलर मॉलिक्यूल इट डज नॉट शो further reaction with phenyl hydrazine molecule. So rest of the hydroxyl groups, they do not respond, because again if we want to react it with phenyl hydrazine, we need to do some addition or some expulsions, and because the first 2 carbon atoms are very well like they are like happy because they are being stabilized by formation of a 6-membered ring, so they do not want to further react and disrupts their stability. So only the reaction occurs only at the first 2 carbon atoms because of the added stability which is being gained by the formation of this 6-membered ring. This is again further explained by taking the example of having a substituted phenyl hydrazine, that is alpha methyl phenyl hydrazine. तो इसमें हमने क्या किया, हमने substituted phenyl hydrazine लिया, अनसिमेट्रिकल फिनाइल हाइड्रोजीन है ये, और इसको हमने किसी कार्बोहाइड्रेट के साथ रिएक्ट करवाया। अब ये कार्बोहाइड्रेट कौन सा हो सकता है? कोई भी ले सकते हैं हम, ग्लूकोज भी ले सकते हैं, फ्रक्टोज ले सकते हैं। हमने यहाँ पे क्या लिया? एल्डोपेंटोस लिया। तो ये 5 मेंबर्ड कार्बोहाइड्रेट है। एल्डोपेंटोस को हम अल्फा मिथाइल फिनाइल हाइड्रोजीन के साथ रिएक्ट करवा रहे हैं, जो कि क्या है? अनसिमेट्रिकली डिस्ट्रीब्यूटेड फिनाइल हाइड्रोजीन है। तो ये क्या करेगा? अब फर्स्ट 2 कार्बन पे तो एडिशन होगा ही, तो फर्स्ट 2 कार्बन पे एडिशन होने के साथ साथ ये क्या कर रहा है? और भी बाकी कार्बन के ऊपर एडिशन कर रहा है। वाई इट इज़ बीइंग एडेड? इनिशियली जब भी ओसाजोन फॉर्मेशन होता है तो फर्स्ट 2 कार्बन के ऊपर बनता है, लेकिन आफ्टर द फॉर्मेशन ऑफ द ओसाजोन, आफ्टर द एडिशन ऑफ दिस फिनाइल हाइड्रोजन मॉलिक्यूल एट द फर्स्ट 2 कार्बन, नाउ बिकॉज देयर इज़ नो फ्री NH ग्रुप इन दिस केस, दिस इज़ अ सब्सटीट्यूटेड फिनाइल हाइड्रोजन। किसी भी नाइट्रोजन के पास फ्री हाइड्रोजन नहीं है, तो फ्री हाइड्रोजन ना होने की वजह से यहाँ पे कोई टॉटोमेरिज्म या यहाँ पर कोई भी हाइड्रोजन बॉन्डिंग की पॉसिबिलिटी नहीं है। So because this structure is not being stabilized by the hydrogen bonding, it does not form any 6-membered intermediate structure. तो ये स्टेबिलिटी नहीं मिल रही, तो रेस्ट ऑफ द हाइड्रोक्सिल ग्रुप्स आर ऑल्सो ईजिली एक्सपोज्ड एंड they also react with the another molecules of phenyl hydrazine, unsubstituted phenyl hydrazine molecule, and it will form compound until all the hydroxyl groups are being replaced by this hydrazine molecule. So keep it in mind that this type of compound is not an osazone. This is a simple addition molecule, but this is not an osazone molecule. Okay, and osazone formation is a very common reaction for all the monosaccharides. जितने भी हमारे मोनोसेक्राइड्स मॉलिक्यूल्स होते हैं, या अल्फा हाइड्रोक्सी कीटोन या अल्फा हाइड्रोक्सी ऑल्डिहाइड्स, ऑल दीज मॉलिक्यूल्स दे फॉर्म ओसाजोन. ओके, एंड since during osazone formation, as I have already told you, that configuration around carbon 1 and carbon number 2 is destroyed. जो भी configuration होती है वो destroy हो जाती है, क्योंकि ओसाजोन की formation हो रही है. यहाँ पे जो chirality थी वो ख़त्म हो गई. So because chirality is destroyed because of the formation of such an intermediate structure, so any diastereomeric monosaccharide अगर कोई होगा जिसमें कि एक से ज़्यादा chiral centers present है, जो कि कार्बन नंबर 2 पे डिफ़र कर रहे हैं, मतलब कि जो कॉन्फ़िगरेशन है कार्बन नंबर 2 पे सिर्फ वहीं पे डिफरेंस आ रहा है, बाकी पूरा का पूरा स्ट्रक्चर अगर सेम है तो ऐसे मॉलिक्यूल सेम टाइप ऑफ ओसाजोन फॉर्म करते हैं. फॉर एग्जांपल D+ मैनोज या फ्रक्टोज का जो स्ट्रक्चर होता है वो ग्लूकोज से सिर्फ कार्बन नंबर 2 पे डिफ़र करता है. तो ये दोनों ही मॉलिक्यूल जो ओसाजोन फॉर्म करते हैं वो वही ओसाजोन होता है जो कि ग्लूकोज भी फॉर्म कर रहा है. सो द ओसाजोन्स आर सेम, द मेल्टिंग पॉइंट, द बॉइलिंग पॉइंट, वट एवर द फिजिकल प्रॉपर्टीज आर देयर, it will be same for the osazone of glucose, mannose and fructose. Okay, so we can say that C2 apamers, they differ only in configuration at C2, they give same osazone. Alright, so this is all about the osazone formation. I hope you are able to understand. If there is any query, you can always message me. You can leave a message in your Google Classroom. I will definitely try to clear all your doubts. Please listen to this video until all the points are clear. I am going to ask all the questions in the live class. Thank you.